So let's start with the second algorithm. Here to help the discussion, let's consider two matrices. Let's say the input matrix that we want to find the clusters in. Let's call that inmat. And let's choose a particularly simple example for that so that we can track the changes and understand the algorithm better. So let's say we have 1 0 0 and 0 1 1. So you can see that this one has two clusters. One is here and the other is this. We introduce another matrix which we call countmat or cmat in short, and this to begin with is going to track all the unique non-zero elements that inmat has. So essentially all the different ones, but we give them different numbers. So it would be 1 0. So this one is 0, and then this one is the second one, and then this is the third one. So we as usual have the four moves, which are again up, down, right, and left. So this time, in contrast to the last algorithm, we are not going to check these moves based on each element, but this time we are going to move entire rows and entire columns. So we are going to get new matrices each time we apply these moves. So we would for example move the, so when we are applying say the right shift, so we would move this column one place to the right, this column one more place to the right, and this column would go all the way here, would get this new place. So the other thing that I would like to quickly point out is that you take any matrix and you apply all these moves, up, down, left, right, and you end up with the same matrix. So if you apply all four of them, then nothing changes. So that's something that we are going to apply, that knowledge we are going to apply in this algorithm. So all right, so the reason for, you might be wondering why we have this cmat, this matrix, what purpose it's going to serve. Now we are going to track whatever operation we are going to do on inmat. We are going to track that change on cmat as well. It's kind of it's going to mirror all the difference that's happening here, and our idea is, as we apply all these different shifts, we are going to try to change all the different unique numbers, but which the numbers which happen to be adjacent, to turn them into one single number, and at the end we would see how many unique numbers we have. Remember, at the time, if we do all these things correctly, then all the adjacent numbers will be just a single number, not like now where 2 and 3 are different, and all those unique numbers would give us the number of clusters. So that's the basic idea that we have. And when we are talking about these shifts, up, down, left, right, we are going to use this function called circ shift, which has been suggested in the exercise. Alright, so now let's apply a shift to the right and see what happens, how we are going to bring all these different numbers in cmat into the same number, and what we are going to do. So let's say we apply shift to the right and we get two new matrices. So for this one from inmat, 1 0 goes to the middle row So 1 0, uh, 0 1 goes to extreme right, and this 0 1 it goes all the way to the left, so it becomes like this. We call this new matrix IC, and we apply the same shift on CMAT, and we call that just C. So for C, we are going to have 1 0 comes in the middle, 0 2 goes to extreme right, and 0 3 comes back to extreme left. So once we have InMat and also its changed version IC, and CMAT and its changed version C, we are going to do some logical comparisons. We are going to compare these matrices element by element and see what we understand from there. So first I would like you to see, imagine IC and InMat overlap. So when you do that, you compare if each position, if it is if both of them are non-zero, and what that means. So you'd consider here, for example, the same position, it's 1 ampersand 0. If you imagine that operation, you see that it's false, and you can do that for each position. You'll find that except this one, all positions are uh, would give you logical false. So what that means? That means we have identified presence of one cluster here, because we move to the right and we do not overlap with 0 at that specific position. So that means before, to the left of this position, we had another one. So now we want to do the same thing on this side, between CMAT and C, but here notice that we have different numbers. So we are going to do not only this logical comparison, which would give us something very similar, but we can also compare whether this number in this position, this number CMAT in CMAT, whether that's bigger or smaller than that in C in the same position. And if so, we can decide beforehand that, well, if it is say bigger, then we are going to change that. So let's keep that aside for the moment. So we can see that if we do the same logical comparison position by position, all these would give us false. However, this position would give us that in CMAT this position is bigger than C. And so we write, for the time being, we compare CMAT is greater than C. And for this part, we compared InMat and IC, and we notice that the non-zero elements here, that tells us that we identified a cluster. So if we combine these two, that is this, so in that case we find the corresponding true element from here and the element which is bigger in CMAT compared to C. And if we combine all those information, then we can choose, let's say whenever that happens, we are going to make CMAT this number same as whatever we found in C. So if we do that, then we would have CMAT change into a new CMAT, which will be 1 0 0 0 2 2. Then we move on to the next move. So let's say now we go to the left, or we complete all the moves, and as a result, at the end of it, we will have a modified CMAT, and at the end we are of course not changing in mat, but you can see from here that the different numbers that were there in CMAT to begin with, uh, depending on all the different shifts, all the adjacent numbers would be changing, but this logic is going to bring them into the same number. So at the end of all these 4 different moves, we compared the final CMAT with whatever we started before we started this loop, and then see if it is same or not. If it is not the same, then we store the new CMAT and repeat this procedure of going through all these different moves and see if it changes further. So once CMAT stops changing, then we know, like, I mean, stops changing after going through all these 4 different moves, then we know that we have identified all the different clusters, because just going through 4 different moves would not change CMAT anymore. And I mean, if it passes through once without change, that means it's not going to change any further. And then of course we can read off all the different elements, and from there all the unique elements in CMAT, and this time all the adjacent ones would be the same number, and from that we would be able to identify the number of clusters. So now let's go to the program, and I would explain how this is implemented along with some nifty tricks, and you will see the applications of, for example, functions all and unique there, and we will probably understand better.